Hello and welcome to the Discrete Mathematics course in the Department of Computer Science at Tennessee State University. My name is Ali Sekman. I'm a professor of computer science here at Tennessee State University. Today we are going to talk about propositional equivalencies. In other words, we are going to show that if two compound propositions are logically equivalent, we can replace one with another one. Let's get started. Okay, so this is Comp 3010, Discrete Mathematics, and this is the second lecture on foundational topics of logic and proofs. In the last lecture, we talked about propositional logic and its applications. Today, we are going to talk about propositional equivalencies. Equivalences, actually, we are going to show that if we have two compound propositions, if one is logically equivalent to another one can be safely replaced with the other one. And next lecture, we'll talk about predicate logic and quantifiers, universal and existential quantifiers. We'll then introduce the rules of inference, and we're going to use rules of inference to show that different methods of proving mathematical statements. Okay, so now I'm going to remind you what a compound proposition is first. If you recall from last lecture, a compound proposition is constructed using existing propositions with certain connectives. So basically, it's an expression formed from propositional variables using logical operators such as OR here. So P or Q naught is a compound proposition. Compound propositions can be sometimes tautology. Tautology means regardless of the propositional variables truth or falsity, the compound proposition is always true. Or a contradiction, again, regardless of the propositional variables truth or falsity values, the compound proposition is always false. That's a contradiction. Okay. So here is first example. Think about this P or P naught. Well, P or P naught is a tautology. P and P naught is a contradiction. Why? If we have P can be true or false. P naught is false and true. If P is true, P naught is false. If P is false, P naught is true. And P or P naught. Now, think about this. True or false is what? True. False or true is what? True. So this means regardless of the value of P, whether true or false, P or P naught is always true. That's a tautology. Similarly, if we have true and false, then we get what? False here. If it is false and true, we get false here. So in other words, regardless of the value of P, true or false, P and P naught is always false. That means that's a contradiction. Okay. Here is another example. I want to solve this one with you so that we can have a little bit practice together. And if you recall, we have P, Q, two variables. And in order to construct truth table, we list all possibilities: true, true, false, false, true, false, true, false. So we have four possibilities for P and Q. And now here I have a compound proposition right there. First, I'm going to take care of that one. P and Q. Obviously, that's true, false, false, false. Then I have another compound proposition right there. So I'm going to write it down. P and Q implies P. Okay. So P and Q is here. P is here. Imply is in this direction. In other words, we have premise true, conclusion true. So that means the compound statement will be what? True. Here, if the premise is false, you see in those three premises false, no matter what the conclusion is, if premise is false, conditional statement is always true. So I have true, true, true. As you see here, regardless of what P is, regardless of what Q is, P and Q implies P is always what? True. So therefore, that's a tautology. Okay. Here's another example. Let's do that together. 2P, Q, again, true, true, false, false, true, false, true, false. First, let's take care of this compound statement, which is P and Q. That is true, false, false, false. Why? Because that's and true is true, true and false is false, false and true is false, false and false is what? False. And then there's another compound statement right there, P implies Q. Let's take care of it. P implies Q. Well, here that's very easy. This is the premise, this is the conclusion. True, premise is true, conclusion is true, therefore this is true. Premise is true, conclusion is false, therefore this is false. Here, premise is false. No matter what the conclusions are, the compound proposition will be what? True, obviously. Then we have the third compound proposition right there. So I'm going to say P and Q implies P implies Q. So now, well, this is easy too. We have this guy, and implies is in this direction. So this is the promise, this is the conclusion. So it will be true. Here, the promise is false. You see, no matter what the conclusions are, if promise is false, the compound statement or the conditional statement will be what? True. As you see here, no matter what P is, no matter what Q is, the compound statement is always what? True. So therefore, that's a tautology. Okay, if a compound statement is neither tautology nor contradiction, that's a contingency. That's the definition. And most of the compound statements are contingency, obviously. For example, when we have P biconditional Q, what does that mean? We have P, we have Q. If you recall, biconditional, true, true, false, false, true, false, true, false. This was true if both of them are the same. If both of them are true or both of them are false. If one is true, the other one is false, this is false. As you see here, this is neither tautology nor a contradiction, okay? Logical equivalencies, this is very important. I believe they mentioned about this in the last lecture. Compound propositions that have the same truth values for all possible cases are called logically equivalent. What does that mean? Well, if you have a truth table for two compound propositions and list all possibilities for P and Q, and if the truth tables turn out to be the columns corresponding to the compound proposition turns out to be the same, that means they are logically equivalent, okay? And this is how we represent it, P equivalent to Q, okay? Logically equivalent. So what does that mean? I will talk about this in a bit, okay? For example, let's show that, let's do this together. My notation is P or Q inverse. As you know that this is equivalent to that. And here my notation is P naught and Q naught. So we are going to show that P and Q, sorry, P or Q inverse is equivalent to P inverse and Q inverse. Pay attention. I get the inverse of P, I get the inverse of Q, and or becomes what? And. That's what I'm going to show. I'm going to show that they're equivalent. So here P, here is Q. Okay, true, true, false, false, true, false, true, false. And then I will get P naught first, and then Q naught, okay? And if it is P naught, this is false, false, true, true. Why? True becomes false, true becomes false, false becomes true, false becomes true. And then Q naught is false, true, false, true. Why? True becomes false, true becomes false, false becomes true, true becomes false, false becomes true, okay? And then I'm going to do this, P or Q. P or Q, true or true is true, true or false is true, false or true is true, false or false is false. Therefore, this is true, true, false, sorry, true, 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 and false. Okay. And now I'm going to get P or Q inverse. It will be false, 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 true. Why? It is opposite of this column, right? And then I'm going to go and do this P naught or and Q naught. Well, as you see here, this is P naught, this is Q naught, and I'm going to do and false is false. False and true is false. True and false is false. True and true is true. Therefore, this is F, F, F. As you see here, for all possible combinations of P and Q, we obtain exactly the same column values. Therefore, P or Q, inverse of P or Q is equal to inverse of P and inverse of Q. This is called De Morgan's law, one of the De Morgan's law, as we will see now. Okay. And here is what it says. This is important. You must know this. If you want to get the inverse of P and Q, you get the inverse of P first, you get the inverse of Q, and N becomes OR. Okay. And if you want to get the inverse of P or Q, you get the inverse of P, you get the inverse of Q, then OR becomes AND. Okay. With my notation, I say P and Q inverse is equal to inverse of P, inverse of Q, and becomes OR. Or similarly, P or Q inverse, inverse of P, inverse of Q, and OR becomes AND. Okay. So in general, if you have, for example, P1 and P2, and if you have AND statements, and if you want to get the inverse of it, you get the inverse of each one. Okay. And becomes OR. Similarly, if you have AND statements with OR, like this, you get the inverse of each, and OR becomes AND. Okay. So that's what it is. Sometimes we can show it with another notation. Okay, here it is. For example, if you want to get the inverse of P1 or P2 or Pn, you get the inverse of each one, and then OR becomes what? AND. Or you can use this notation. This means P1 to all the way Pn. You have a compound statement P1 to Pn. They're all connected with OR operations. If you want to get the inverse of it, you do this way. Similarly, for AND, you get the inverse of each one, and then AND becomes OR. Okay, so that's called De Morgan's laws. We are going to use them left and right. You need to get familiar with those. Okay, another one this is going to be very commonly used. Don't ever forget this. P implies Q is actually logically equivalent to P naught or Q. This is a very well-known equality or equivalence. So therefore, I want you to know this by heart. P implies Q is equivalent to P naught or Q. Why? Let's do it. It's pretty simple. We have PQ, okay, true, true, false, false, true, false, true, false. Then P implies Q, as you already know, this is true, this is false, this is true, this is true. That's what we know. And P naught is false, false, true, true. Why? Because I'm getting the opposite of this column, right? And then I have P naught or Q. Well, here is P naught, here is Q. True or false is what? True. False or false is false. True or true is true. False or true is true. Look here and look here. They are exactly the same column, right? So therefore, P implies Q is equivalent to P naught or Q. You got to get yourself familiar with this. Okay, this is another important law, distributive law. What does that mean? You see, P or Q and R in parentheses, you can distribute this like this, P or Q, and then P or R, okay? So P or Q and P or R. So how do you show that they're logically equivalent? I guess it's right there, so I'm not gonna do it from scratch. We have three variables. Well, maybe I should do it from scratch. Hold on one second. Okay, so that because since we have three variables, I'm just gonna do it from scratch so that we remind ourselves how to do this. We have P, we have Q, we have R. We have three variables. So how many possibilities do we have? If we have three, it's 2 to the 3, which is 8 possibilities. I'm going to list them true, 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 4 true, and 4 false. And then 2 true, 2 false. And then 1 true, 1 false. So these are all all possibilities with three propositional variables. Then I'm going to take care of Q and R. And Q and R, this column and this column connected with AND. So I'm going to be doing this fast. True, false, 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 true, false, okay, false, and false. Then I will say P or Q and R, right? Okay, here is P and here is Q and R, and I'm going to connect them with OR. True or true is true. True or false is false, and so on. So I'm just going to go and true or false is true, true or false is true, false or true is true, false or false is false, false or false is false, false or false, right there, okay? Now I'm going to do P or Q. Well, this is P, this is Q. I'm going to connect them with OR. So true or true is true, true or true is true, true or false is false, sorry, true, okay? True or false is true, false or true is true, false or true is true, false or false is false, false or false is false. Then I will do P or R. Well, this is P, this is R, true or true is true, true or false is true, true or true is true, true or false is true, false or true is true, false or false is false, false or true is true, false or false is false. Then I will connect this to P or Q and P or R. That means this row and this row with AND. True and true is true. Okay, so I made a mistake somewhere, most likely. P or, yeah, P and Q and R, this is supposed to be true, obviously. Okay, true. And then true and true is true. True and true is true. True and true is true. True and false is false. False and true is false. False and false is false. And if you look here, and if you look at here, that means they are exactly the same. So they are equivalent right here. Okay. So don't ever forget this distributive law. And if it is P or Q and R, what do? First, you do this, P or Q, and then you do that, P or R, and connect them with AND, okay? Similarly, if it is P and Q or R, you do that first, P and Q, and then you do the second, P and R, and connect them with OR, okay? That is distributive law. which is the second one is right here. I'm not going to do that, but here and here, the first one, second one, and you connect them with what? Or. And again, you can do it by yourself. That's pretty easy. Once you do that, you're going to see that this column right here and this column right here are exactly the same. That means they are logically what? Equivalent. Okay, key logical equivalencies. Let's talk about this. Identity laws. P and true is always P. Why? Well, it's pretty easy. Look here, you have P, okay? P can be either true or false, right? And then if you have true, that means this is P and true. True and true is true, false and true is false. So that means, as you see here, whatever P is, P and true is exactly the same. So that means P and true is P, okay? Similarly, if you have P can be either true or false. And if you have false, and if you look at P or false, true or false is true, false or false is false. As you see here, true, false, true, false. So that means whatever P is, P or false is always P. So therefore they are what? Logically equivalent. So these are important equivalencies. You gotta know them by heart. P and true is P, P or false is P. This is identity law. Domination law. Well, P or true is true. If we have one true, regardless of what P is, if you connect P with true via an OR operation, you get what? True. So if you don't see it immediately, you can always construct what? Truth table. You have P can be true or false, and then you have true, and this is P or true. True or true is true, false or true is true. You see here, regardless of what P is, you always get what? True. Similarly, if you have P, true or false, and if you have false here, then you have P and false. True and false is false, false and false is false. As you see here, regardless of P, you always got what? False. Idempotent law, well, P or P is P, P and P is P. I mean, that's very clear. So I don't need to say anything about it. P or P is P, P and P is P. Double negation law, what does this say? This says inverse of inverse is itself. In other words, if you get negation of negation, it is itself, okay? That's also very intuitive. Well, this says P or P naught is always true. And that's obvious, right? If P is true, P naught is false. True or false is true. If P is false, P naught is true, and false or true is always true, okay? Similarly, if P is true, P naught is false, true and false is false. If P is false, then P naught is true, false and true is false. So that's always false. Get yourself familiar with this. I have another slide right there. If you look here, P is true or false. P and true and true is true. Okay, false and true is false. Similarly, true or false is true. False or false is false. P and false, true and false is false. False and false is false. And how about this one? P or T, P or true. True or true is true. False or true is true. P or P, true or true is true. False or false is false. Similarly, true and true is true. False and false is false. So as you see here, look here. What does this say? This says that P and true is equal to P. As you see here, this is P and this is P. Similarly, this is P, this is F, this is true, this is P, this is P. That's another way of looking at to the previous slide. Okay, so this is commutative laws. Whether P or Q or Q or P are obviously the same. P and Q or Q and P are the same. Associativity laws, this is important. For example, here P and Q and R. Well, as long as these are all and, you can put the parentheses anywhere you want. Or as long as they are or, you can put the parentheses anywhere you want. That's associativity law. But this one is important, distributive laws. See here we have and, or, but now we have or and. Now we need to be very, very careful. We have to distribute this. P or Q, P or R connected with and. Here, P and Q, P and R connected with or, okay? Absorption law, this is also pretty easy. Well, you have P or P and Q. Well, look here. Look here. Let's assume that Q is true. If Q is true, P and true will depend on P, and P or P will be P. If Q is false, P and false is what? False, and P or false is P. So that's the case. So you can easily check those, and P or Q is also P. This is called absorption law. Maybe we'll have a proof of it. Here you go. Actually, we can show the proof very easily, either using truth table or directly, but let's do it with truth table here. We have P, we have Q. First, P and Q is right there, and then P or P and Q is right here. P or V is here, and then P and P or V is right there. As you do it by yourself, you're going to see that this column and this column are exactly the same, okay? And it is the same as what? P here, okay? This is P, so that means this must be P, and this must be P, okay? So this guy is equivalent to P, and this guy is equivalent to P, okay? Okay, here are some more equivalencies. Well, we have already seen this one. We already did this one. You need to get familiar with it. This is extremely important. And this is contrapositive from last lecture, if you remember, contrapositive. P implies Q is equivalent to Q naught implies P naught, okay? For example, think about this way. If it rains, I stay home, okay? If this is P, this is Q, P implies Q. This is the same as saying Q naught implies P naught. This means if I do not stay home, then it does not rain. So if it rains, I stay home is equivalent to if I don't stay home, then it does not rain. They are exactly the same thing, okay? So we can easily show them. I mean, if you're not sure, you can easily show using the truth table. For example, let's do this. Let's remind ourselves very quickly. P, Q, true, true, false, false, true, false, true, false, okay? And then let's do P implies Q. We know that this is true, false, true, true. And P naught is false, false, true, true. And then P naught or Q, what we are going to do, this is P naught, this is Q. We connect them with OR. So then obviously we get true, false, true, true. So look here and look here. They are exactly the same. So they must be equivalent. okay? And you can pick any one of them and then you can prove, but you gotta get yourself familiar with them. If we are not sure, for example, if you're not sure about any one of them, you can prove, but let's review. P implies Q is equal to, I write it again, P implies Q is equivalent to P naught or Q. This is very important. P implies Q is equivalent to Q naught implies P naught. Get familiar with that, okay? P or Q is equivalent to P naught implies Q, okay? And P and Q is equivalent to P implies Q naught, okay? And these are all involving conditional statements and so on, okay? You don't have to memorize, but they're gonna be very handy for us. P implies Q and P implies R means P implies Q and R. If P implies R and Q implies R, P or Q implies R. P implies Q or P implies R, then P implies Q or R, okay? Look here, this guy and this guy. They are almost the same, right? This is and, this is or. Okay. And biconditional, biconditional statements. Well, again, this one, how do you prove those? I mean, it's very easy. You say P, you say Q, okay? True, true, false, false, and then true, false, true, false. And then we have P in double biconditional. Q is true, false, false, true. That's what we know. And then you can say P implies Q, okay? P implies Q is true, false, true, true. And then you can have Q implies P. Q implies P. You do from this one to this one in this direction. True, false is true, and false, true is true. True, false is false. False, false is true. Okay. And then you connect them with and. True and true is true. False and true is false. False and true. As you see here, they're equivalent. In fact, this makes sense. Why? P biconditional Q means P will imply Q and Q will imply P. Okay. And P biconditional Q is equivalent to P naught biconditional Q naught. Okay. So these are, of course, you cannot memorize, but you have to get familiar with those. Okay, so let's show that sometimes we can use truth table, sometimes we don't have to use truth table. Look at here. For example, P implies Q naught. Okay, what does that mean? If you recall, this was equivalent to P naught or Q, right? If we go a couple of slides, right here, I'm using this identity or this equivalency. P implies Q is equal to P naught or Q. So here, P implies Q is P naught or Q. And then I will use the distributive law. Distributive law says P naught, and then Q naught, and connect with an and, or becomes and. And inverse of inverse is what? Itself, and then Q naught. As you see here, this guy is equivalent to this guy right here. So this one is equivalent to this one. Okay, again, let's use the book's notation here. The inverse of this, again, P implies Q is replaced with P naught or Q. And then the inverse of inverse, and then inverse of Q, that's the Morgan's law, and then or becomes and then this is it. How about this guy? This guy is not too difficult either. It says P or Q naught and, sorry, P or P naught and Q inverse. That's what it is asking, right? So I'm going to shade, I'm going to tell that I'm going to do this one, the inverse of P, and then the inverse of this statement, and here or becomes what? And, okay, right there. Then I will leave this P naught, and here I will take the inverse of inverse and inverse of Q, and this and becomes or, okay? So here P inverse and inverse of P is what? Inverse of P is P or Q naught, right? And then I will use the distributive law. I will say this is P naught and P, okay, or P naught and Q naught. And what is P naught and P? This is always false. So that means false or P naught and Q naught. And this is equal to false or something is that something, P naught and Q naught. As you see, this statement right here is equivalent to this statement right there, okay? And here how we can do it step by step. Okay, and we can do this in different ways. Let's remind ourselves, if we have X implies Y, this is equivalent to what? X naught or Y. Okay, again, I'm going to all the way here. I have this statement right there. P implies Q is equal to P naught or Q. Okay, so now think about this. This is X and this is Y. Okay, so I'm going to do this. I will say this is equivalent to P and Q inverse or P or Q, right? So X implies Y is equivalent to X naught or Y. And here I will get the inverse of this or, and then this one. And the inverse of this guy will be P inverse or Q inverse. The inverse of P, inverse of Q, and becomes or, right? And then I have or P or Q. Well, I mean, since we have or, we can put the parenthesis, we can, for example, I can switch this to, I can say Q naught or P naught. That's the same. And I can say P or Q. And I can put parentheses anywhere I want. This is equal to what? P or P naught is always true. So this becomes Q naught or true or Q. Well, Q naught or true is always true. Then becomes true or Q. True or anything is always true. As you see, that's a tautology. No matter what P is, no matter what Q is, we always get what? True. Okay, so this concludes this short lecture. I hope you enjoyed it. It's extremely important that you feel comfortable with compound propositions, how to construct compound propositions from atomic propositions, and also you should feel comfortable to show that two compound propositions are logically equivalent. You have to get familiar with those. I'll see you in the next video.